Hello, my name is Shervin Bagheri. I am a professor in fluid mechanics at KTH, and today I'm going to talk about transfer of mass and momentum at the interface between porous media and free flows. This is a work in collaboration with Ujis Latsis and Suraka Yogarai, who is in India currently. So, as you may have seen already in this conference, there are a lot of problems which involves the transport of momentum, heat, or mass from one medium to the other. And here in particular, we're interested in these transport problems from a free flow to a porous media or vice versa. So of course, this transport can happen through different mechanisms. It could be advective mechanisms or molecular transport. And it is of interest to be able to predict this transport phenomenon through high precision estimates of friction factors and transfer coefficients, in particular using upscaled effective equations in order to be able to tackle more complex three-dimensional problems. Now, our approach is effective two-domain representation of this problem. So in the free flow, we have Navier-Stokes equations. In the porous domain, we have an effective equations, for example, Darcy's law, and coupled with continuity. And between these two domains, there's an interface, and the problem here is to find appropriate conditions at this interface in order to couple these equations. Now, there's a lot of work on this. It started already in 1967 with the so-called Beavers and Joseph condition, and is still an active field today. However, there exists no universal or final version of these interface boundary conditions that works for every problem. However, what one can achieve through different mathematical frameworks is a formalism. So what would one like to have from a formalism or a framework? These are 5 criteria that we are particularly interested in when we want to use this in applications. So precision is important. We would like to be able to tune the precision depending on the problem. The link to the microscopic features of the porous material is important. We would like to have a non-empirical method, meaning that there needs to be no experimental data fed into our model. We would like to have a physical system such that we can understand the conditions and relate them to the governing equations. And of course, accessibility is important. So we would like to be able to rather straightforwardly implement and use these conditions. So the framework we propose is based on multiscale expansion, and it's really summarized in this sketch here. So you start off with your physical problem. And the first thing you need to do is use your physical understanding of this problem to find a good scaling. So this is absolutely crucial because it's going to determine your final interface boundary conditions. Now, once you have chosen these scalings, you squeeze it into this multiscale machinery, which through a sort of a standard procedure provides you with a set of boundary conditions. Now, these boundary conditions can be way too complex to implement or to understand. So you can impose constraints such as mass conservation, obviously, but also boundary conditions and symmetry, and some handpicking, actually, in order to reduce the complexity of these boundary conditions such that they are useful for practical problems. So in this talk, I'm going to walk you through these steps for a particular problem. Before I do that, I would like to mention the assumptions that this framework is valid for. And the 3 major ones are that the porous media has to be periodic. It can be layered in the normal directions to the interface, as you can see here with these skewed ellipses. However, in the tangential, wall parallel, or interface parallel directions, we assume a periodic media. There has to be a length scale separation between the characteristic macroscopic length scale H and the pore length scale L, and also the viscous effects have to dominate near the interface, where the Reynolds number has to be below 1. Now, the problem we are interested in particular is shear dominated flows. Here you have 2 examples. Now, as I said, choice of scaling is very important, and there are many ways of doing this. So for this example, the free flow pressure can be scaled with delta P, where delta P is some characteristic pressure. The free flow velocity is scaled with some macroscopic velocity. Here UF, for example, in the lid-driven cavity, that will be the velocity of the lid. And obviously length scales are scaled with the macroscopic length scale H. Now near the interface in the porous media, it gets a bit more trickier. There are more choices to be made. We choose to, which is pretty standard in shear-dominated flows, to scale the pressure with the macroscopic pressure, but the velocity with US here, where US is the typical velocity of the interface, so the slippage at the interface between the two domains. And the length scales here in the porous domain and near the interface are clearly scaling with the pore length scale. So balancing these different scalings with each other through stresses, you can obtain relationships between them. Now, if we move on, there's this multiscale expansion machinery, which I call this whole formalism, which is a sort of a standard technique. You have to non-dimensionalize your system. You have to expand your quantities. Here will be velocity and pressure in this small parameter, which is the ratio between the length scales, epsilon. Once you have this multiscale expansion, you can expand your governing equations and gather different orders of them, of these governing equations. And that will be followed by surface and volume averaging, which results in your multiscale expansion interface boundary conditions. Now, if you apply this machinery based on this scaling, this is the first order interface conditions that you obtain. So at the interface, you have a velocity, all three components. So it's what I call the slip velocity, but actually it's also the normal velocity. So all the three components of velocity at the interface are proportional to the stress vector on that interface through a tensor L, which has the dimension of the pore length scale, or scales with the pore length scale. Now, this is a classical Navier-Slip type of boundary condition, and which you may have encountered before. For the pressure, there is a pressure jump at the first order, which is also proportional to the stress vector through the pressure jump vector B. Now, this boundary condition has, both of these boundary conditions have an error of order epsilon. So if your epsilon is very small, you can definitely stick to these boundary conditions. However, if epsilon is not very small, for example, is just below 1, you would need to go a higher order. Now, there are quite a few elements in these two constitutive parameters, L and B. For 3D, you have 12 elements. For 2D, you have 6 elements. And all these elements can be obtained from microscale unit cell problems. In particular, prior to that, before doing that, you can actually remove a number of these elements just by constraints. For example, from mass conservation and symmetry, you can reduce the number of elements from 12 to 5 in 3D and from 6 to 2. At the bottom here is an example of these first order boundary conditions for a 2D system. We see that the tangential velocity ux has one scalar lxx, which has to be determined. The wall normal velocity in this 2D case, or rather in this first order case, is 0, and there's a pressure jump here, which has one parameter which needs to be determined to be 1. Now, as I said before, you might want to go one order higher. In particular, if you want to have a transpiration velocity to capture advective transport of mass and heat in or out of the porous material, in addition to a diffusive one. Now, if you go one order higher, you obtain two terms in addition to the one you had before for the velocity at the interface. One of them is a Darcy-like tensor here, which has this parameter k, which is a second order tensor. And the second term here is a term which is proportional to the variation of shear or variation of stress at the interface. And m here is a third rank tensor. Also, you have two new terms for the pressure jump here, A and C, which are a vector and a tensor respectively. And these can really be considered as some sort of a friction factors where the velocity is transformed into a stress. Now, obviously, in this 3D for the 3D system, the second order interface boundary conditions are way too complex to implement, and to determine all these elements, you have 114 elements in 3D and 44 in 2D. So we would like to reduce the complexity of these. And again, of course, we can use symmetry and mass conservation as constraints. But in addition to that, we can actually handpick terms. And here's a bit of engineering judgment that comes into this. And of course, mathematically, this becomes a little bit or quite inconsistent when you do this handpicking. But this is the way to actually get a set of interface boundary conditions which are highly accurate and at the same time useful and practical to implement. So again, looking at the second order multiscale expansion, you see you have these 5 vectors and tensors, and you can just handpick the ones you like based on physical arguments. So for shear dominated flow, the tangential velocity is really dominated by the first order, obviously, but you really not, at least in our problems, not so much interested in correcting the first order. So we stick with the first order when it comes to tangential velocity. Now the normal velocity first order is 0. So we like to include all the second order normal velocity, in particular if we're interested in transport of heat and mass through advection. Now pressure jump, here we use a mix of coefficients to make this practical and at the same time to be able to keep a good accuracy of our pressure at the interface, in particular in order to be able to estimate the Darcy velocity inside the porous material with the high accuracy. So handpicking these terms is of course a dangerous task, and you have to use your good judgment and a validation of some sort. So here we had the luxury of doing a fully resolved pore scale numerical simulations, which we call DNS, and compare that to this effective 2-domain hand-picked interface condition. So the particular porous structure here are tilted ellipses, which is a layered problem just to increase the complexity, and is a lid-driven cavity here. So if we compare these two methods, what we see if we start to look at the slip velocity at the interface, we see that the DNS and the continuum model compare very well. You see that the continuum model averages out these oscillations that you see in the pore scale simulations, but it follows the solution very well, which really means also there's no need to correct this. It's already pretty good. Now for the transpiration velocity, we use the second order terms, and you see that it follows the DNS pretty well here, and otherwise for first order it would obviously be 0. Nevertheless, transpiration velocity is much smaller than the tangential velocity. It is indeed a high order term. Now, one last point is how to determine all these elements. Even if you reduce them, you still have to determine them to have a non-empirical approach. And really, you do this through a unit cell approach. And the equations of this unit cell are a product of this multiscale expansion machinery. So you don't have to actually come up with these equations. They just come out naturally. And in particular, to solve for these elements, for this particular approach, you need to do 5 Stokes problem, where 2 of them are related to shear forcing at the interface, and 3 of them are related to volume forcing below the interface. So having solutions in these unit cells, you can average them and thus obtain the elements appearing in the effective macroscopic interface boundary conditions. All right, so we have had a wish list for this framework, and that would contain high precision, multiscale, non-empirical, be physical and accessible, and to different degrees I think we have achieved these points. The key message here really I think is to realize that there is no one set of boundary conditions that you can just use from taking from off the shelf. You really need to combine mathematics and engineering to adapt this framework to your problem. And I would like to finish off by thanking the 2 main contributors to this work, which is Ujis, who's still at KTH, a researcher, and Suraka, who's now assistant professor in IIT Goa. Also our funders, I would like to acknowledge, and I'll leave you with some references of papers, codes, and webpage. In particular, both the code and papers are open source. Thank you for listening, and don't hesitate to ask any questions via the Q&A or email me if you want to know more about our work. Thank you.